This lecture is devoted to two-dimensional maps. So it's introduction to two-dimensional maps. So we have now two variables. Each dynamics of each variable is described by a difference equation. So this graphically can be represented as mapping points on the plane. This is x, this is y. Let's say this is point has coordinates x naught, y naught. Then we find x1, x2, and this will be x1, x2, x and y1. So this, after first iteration, we jump to this place. Then we find x2, y2. This will give coordinates of another point of the plane, and this is another iteration, and so on. So this is how we can see it. Now, we already encountered some examples of two-dimensional maps. First example. So you remember Fibonacci model. So in Fibonacci model, it was one variable system. It was in fact one-dimensional map, but second order. So what we had is xn plus 1 equals to xn plus xn minus 1. So what we can do? It is one-dimensional second order map. So we introduce new variable yn, which is xn minus 1, and then xn plus 1 will be xn plus yn, and here I can put it yn plus 1 equals to xn. So this is our two-dimensional map. Next example, also we know, we've seen it before. It is map on the complex plane. So we discussed this when we were considering Mandelbrot sets. So what we had zn plus 1 equals to some function of z. What we considered was zn squared plus c, where zn is complex number and c is also complex number. So since they are complex numbers, we can put zn is xn plus I yn, and c, let's say a plus ib. Xn is real part of zn, yn is imaginary part, and a is real part of c, and b is imaginary part. So if we put it like this, then this transfers into new equation. Xn plus 1 plus yn plus 1 equals to xn plus I yn squared plus a plus ib. So this will be equal to open brackets xn squared plus 2i xn yn minus yn squared plus a plus ib. And now we can separate real parts and imaginary parts in this equation. If this equals to this, then real part should be equal on the left hand side equal to real part on the right hand side, and imaginary parts also. So therefore xn plus 1 will be equal to xn squared minus yn squared plus a, and yn plus 1 equals to 2xn yn plus b. So this way we got two-dimensional 2D map. So now I want to extend our methods which we used for study of one-dimensional maps to two-dimensional maps. So we consider dimensional map xn plus 1 equals to f of xn by n, and yn plus 1 equals to g of xn by n. So this is the map we consider. Now we introduce a few definitions. So definition 1. Fixed point. Fixed point. Fixed point. So point x with the pair of numbers x, y, x capital, y capital, is called a fixed point if from x naught equals to x capital, y naught equals to y capital, it follows that xn equals to x capital and yn equals to y capital for any n. And from here we get straight away to find fixed point. So we follow the following procedure. We solve algebraic system. X equals to f of xy, y equals to g of xy. Yeah, so roots of this system are fixed points. Okay, now next definition, definition 2. So x, y is stable fixed point if for any epsilon there is delta such that from x naught minus x squared plus y naught minus x capital and here y capital squared less than delta, it follows that xn minus x capital squared plus yn minus y capital squared less than epsilon. So what this means? This means that x naught, y naught in delta neighborhood of x capital, y capital. So this is in fact distance from x naught, y naught to xy. And this means that xn yn is in epsilon neighborhood of x capital, y capital. So there is no, well, basically what it means no divergence. So we start in neighborhood of, if our orbit starts at neighborhood of fixed point x capital, y capital, that it's always in its neighborhood, so it's not going away. So this is also called neutral stability. For asymptotic stability, we require convergence. We need convergence. That is x capital, y capital is asymptotically stable if from, well, if there exists epsilon such that from x naught minus x capital squared plus y naught minus y capital squared less than epsilon, it follows that xn yn tends to x capital, y capital. So now we have convergence to the fixed point x capital, y capital. Therefore, x capital, y capital is called asymptotically stable. Now we start analysis of maps, and this whole analysis is based on analysis of linear maps. Therefore, first we consider linear maps. Linear map is like this: xn plus 1 equals to e11 xn plus e12 yn, yn plus 1 equals to e21 xn plus e22 yn. So this is also homogeneous. Homogeneous means we don't have no free terms. If there would be free terms, we could get rid of these free terms by changing variables. I don't want to discuss it now, but it should be pretty much, you can play with this. Okay. Now, if we introduce vector x and y n, let's say u equals to un, it is vector, and we introduce matrix A, A11, A12, A21, A22, then our system can be represented like this: un plus 1, vector un plus 1 equals to matrix A times vector un. So this transfers into this. And now I want to make statement about solution of linear system. Solution is given as un equals to c1 b1 lambda 1 to the power of n plus c2 b2 lambda 2 to the power of n, where lambda 1, lambda 2 are eigenvalues, and b1 and b2 are eigenvectors of matrix A, and C1, C2 arbitrary constants, arbitrary numbers. So now I will prove this statement. So I will prove that solution of this system is given by this expression. Now, since lambda 1, b1, and lambda 2, b2 is eigensolution for matrix A, we have A times b1 equals to lambda 1 b1, A times b2 equals to lambda 2 b2. So this is from definition of eigensolution. So if we introduce matrix B with columns represented by vectors b1 and b2, then matrix A times matrix B is matrix A times, if this is matrix B, this will be equal to AB1, this first column, the second column, A times vector B2. A times B1 is lambda 1 B1, and AB2 is lambda 2 B2, and this can be represented as B1, vector B1, vector B2 times matrix lambda 1, 0, 0, lambda 2. This is, it's easy to check. So this, if we multiply, this is matrix B, in fact, matrix B. B1 times lambda 1 plus B2 times 0. This is first column, and second column is B1 times 0 plus B2 times lambda 2. So this is, in fact, we get. So first column will be B1 lambda 1, and second column will be Yeah. So what we got, what we have proven that A times B equals to B times this diagonal matrix, lambda 1, 0, 0, lambda 2. Now we introduce variable v. So we'll make substitution. So it's simply substitution un equals to b times vn. So all of this is fine. We can do this. If b is non-singular and b is non-singular, if vectors b1 and b2 are linearly independent. Therefore, we consider case when b1 and b2 are linearly independent. Then, with this substitution, what we will have? So we have un plus 1 equals to a times un. Now, un plus 1 is, this is b times vn plus 1. And here we have a times b times vn. Now, if b is non-singular, then we can multiply it from the left by inverse of b. Then we will have inverse of b times vn plus 1 equals to inverse of b times a times b times vn. So this is identity. Therefore, we'll have vn plus 1 equals to inverse of b. And we know that ab is b times d times vn, where d is lambda 1, 0, 0, lambda 2. So it was proven on the previous slide. Inverse of b times b is identity, therefore it will be d times vn. So this is what we got. We got vn plus 1. This is equation in terms of new variable v, d times vn. Now let's see how it goes in step-by-step manner. So v1 will be equal to dv naught. v2 equals to dv1, which is d times dv naught. Now, if we check, so we can put it like this, d squared times v naught. And therefore, we can conclude that vn equals to d to the power of n times v naught. So this is what we have proven so far. So next point is, what is d to the power of n? So d, we know, is diagonal matrix with diagonal entries equal to eigenvalues of matrix A, lambda 1, 0, 0, lambda 2. D squared would be lambda 1, 2 times lambda 1, 0, 0, lambda 2. And this is, in fact, lambda 1 squared, 0, 0, lambda 2 squared. This is easy to check. Check it. And moreover, d to the power of n will be equal to lambda 1 to the power of n, 0, 0, lambda 2 to the power of n. And now now Vn equal to d to the power of n times V naught is in fact lambda 1 to the power of n 0, 0 lambda 2 to the power of n times V naught. And V naught, let's represent V naught in this way. So it has component C1 and C2. C1, C2. C1 and C2 arbitrary. And therefore C1 and C2 are arbitrary constants. And this, if we multiply these two matrices, we will get C1 lambda 1 to the power of n, C2 lambda 2 to the power of n. And finally, since un is b times vn, or it is b1, b2 times vn, this will be equal to b1 times vn. No, let's put it like this. Then we can put it like this. It is b1, b2, and here we'll put this c1 lambda 1 to the power of n, c2 lambda 2 to the power of n. And then after multiplication, we will get b1 c1 lambda 1 to the power of n plus c2 b2 lambda 2 to the power of n. And this is our proof is completed at this point. So what we have proven? We have proven that the map un equals to un plus 1 equals to a times un has solution given, so we have analytical solution for this. Un is c1 b1 lambda 1 to the power of n plus c2 b2 lambda 2 to the power of n. And now let's consider what happens for different matrices A. So first case, we will consider lambda 1 and lambda 2 are real. So A has real eigenvalues. So, and then this is case 1. And in this case 1, we will consider subcases. Subcase A. Lambda 1 by absolute value less than 1, and lambda 2 by absolute value less than 1. So in this case, if lambda 1 by absolute value less than 1, then lambda 1 to the power of n tends to 0. Lambda 2 by absolute value less than 1 means lambda 2 to the power of n tends to 0, and therefore un tends to 0 vector. What we get here? We get un plus 1 equal to aun. So this is anyway has fixed point 0, 0, and this fixed point is stable. So this is what we conclude for this case, and we introduce a definition here. If lambda 1 by absolute value less than 1, lambda 2 by absolute less than 1, lambda 1, lambda 2 Then K00 is called stable node. And it is also called attractor or sink or attractor, so any term good here. So there is another case. If lambda1 by absolute value more than 1 and lambda2 by absolute value more than 1, then it is opposite. Lambda1 to the power of n by absolute value, let's say, tends to infinity. Lambda2 to the power of n by absolute value tends to infinity. And 0, 0, let's put it like this. Un, vector un tends to infinity, length of vector un tends to infinity, and therefore 0, 0 is unstable. And in this case, it is called unstable node. Repeller and source. We will call it unstable node mostly. I will call it. We can call it also repeller. Source is more common for flows. We will discuss it later. And last case. Last case is when lambda, when one of lambdas absolute value more than 1 and another one absolute value less than 1. Doesn't matter what. Then lambda1 to the power of n tends to infinity. Lambda2 to the power of n tends to 0. And generally, un by absolute value tends to infinity because un is c1 lambda1 to the power of n b1 plus c2 lambda2 to the power of n b2. So this tends to infinity and this tends to 0, and therefore un will tend to infinity. And in this case, 0, 0 is called saddle point. What it means, let's consider it in more details. So this is x, this is y, so we have 0, 0 here. Let's say this is b1 vector. Let's assume this is b2 vector. It is, they could be a bit different, doesn't matter. Now, if we have a point, this point, c1, c2, this point, then what happens? We can take this vector, which is, we remember it's vector v0, we can find its components in here and in here. This will be c1, c2. Let's put this. This is some point v0, u0. So this is vector u0. It has component c1 along vector b1, c2 along vector b2, because you remember, so u0 is c1 lambda1 to the power of 0. It will be 1. It will be c1 b1 plus c2 b2, and therefore c1 is here and c2 is this vector. this vector C1, B1, this vector C2, B2. And now what happens if lambda1 if lambda1 is more than 1, then this component will move up. So here we will have C1, lambda1, B1, somewhere here, somewhere 0, further on, C1, lambda1 to the power of n, B1 will tend to infinity. Therefore, C1, lambda1 to the power of n tend to infinity. And this means that we will have motion along this vector, this way or this way. And same concentration along C2 shows that it will be convergence in this direction. So what we have, so if this U naught will go here, it will be U1. So U1 will have shorter component along vector B2 and longer component along vector B1. And this way, we can expect that it will be some kind of this motion. So these points will represent the orbit. Or so if this is lambda1 and lambda2 positive, if this is negative, it will be moving up and down. So you can consider these cases. But anyway, so we have convergence in one direction. In the direction of B2 and divergence in the direction of B1. So it's called saddle. So generally we consider all three cases for lambda1, lambda2 real. And on the next lecture, we will consider the case when lambdas eigenvalues of matrix A are complex numbers.